In this video, we're going to consider the role that data visualization plays within a larger data science workflow. As a data scientist, visualization is going to be a key part of your work. You'll use visualizations to rapidly explore new datasets, to understand their structure, and to establish which types of model might be suitable for the task at hand. Visualization is also vital during model evaluation and when checking the validity of the assumptions on which that model is based. These are relatively technical uses of data visualization, but graphics have a much broader role to play within your work as a data scientist as well. When they're designed well, plots, tables, and animations can tell compelling stories that were once trapped within your data. They can also intuitively communicate the strength of evidence for your findings and draw attention to the most salient parts of your argument. Data visualization is sort of an amalgamation of science, statistics, graphic design, and storytelling. It's really a multidisciplinary activity, and that means we have to draw on all of our skills to ensure that we do it successfully. While there are certainly ways to go wrong when visualizing data, there are many more ways that you can get it right. This video won't be a step-by-step tutorial of how to visualize any particular type of data. That's simply not possible. There are too many combinations and too many things that you can do. Neither will this video be a lineup of visualizations gone wrong. There will be one or two of those, though. Instead, what I'm hoping to do here is to pose some questions that get you thinking critically about exactly what you want from each graphic that you produce. So there are 5 things that I'm going to suggest that you think about when producing any sort of data visualization. In this video, we'll consider each of these in turn, starting off with the tools that you use to produce the visualization. When you think of data viz, you might immediately think of some impressive animation or complex interactive dashboard that allows the users to explore the relationships within the data for themselves. These tools are no doubt impressive, but they're by no means necessary for an effective data visualization. In many cases, you don't need any technology at all. The history of data visualization massively predates that of computers, and some of the most effective visualizations remain analog. An ideal example here is this visualization of a year's worth of coffee consumption. Alternatively, the number of cups of coffee consumed every day could have been displayed in a bar chart or a line graph. That would have been a more accurate way to collect and display this data, but it wouldn't have had the same resonance or impact, and it certainly wouldn't have been as memorable. So here we have another example of an analog data visualization. Here, each member of a department has been invited to place a Lego brick onto a grid to indicate how much caffeine they've consumed and how much sleep they've had. The beauty of using Lego bricks here is that they're stackable. So as data is collected, a bar plot is created over 2 dimensions. A third example of this sort of physical data visualization can be found next to the tills in many supermarkets. It's often the case that each customer that makes a purchase is given a token as they pay for their goods. They can then drop this token into one of 3 large Perspex containers as they leave the shop, and each of these boxes represents a different charity. At the end of each month, £10,000 gets split between those 3 charities in proportion to the number of tokens. Because the containers are made from a transparent material, as the month goes on, you can see how the tokens are distributed between the 3 charities, giving an interactive visualization of the level of support for each of the charities. There are, of course, many other ways to construct a physical or analog visualization of your data, and this doesn't have to be done as part of the data collection process. The simplest and perhaps most obvious of these is to create a plot of tabular data using a pen and paper. As well as analog methods, we also have digital tools for data visualization, and here you have a plethora of options. The most similar to pen and paper plotting would be to draw your visualizations using software like Photoshop, or an open source equivalent such as Inkscape. The benefit here is that if you misplace a line or a dot, you can correct this small error without having to start all over again, like you would in an analog version. There are then more data-focused tools that have point-and-click interfaces. These are going to be things like Excel's charting tools, or specialist visualization software like Tableau. These tools are really great because they scale with the quantity of data that you have. So you can plot larger amounts of raw data values that you wouldn't have had the time or the patience to do by hand, whether that was done in an analog or a digital format. These analog and point and click approaches to visualization have the shared limitation of not being reproducible, at least not without extensive documentation that explains how the graphic was created. You can resolve this reproducibility issue by using code to create your visualizations. This has the additional benefit of including visualization as part of your larger reproducible workflow for data science. These scripted visualizations also scale easily with large datasets and are easy to alter if any changes are required. The downside here is that there's a relatively steep learning curve to creating such visualizations, which is exactly what the point and click methods were trying to avoid in the first place. No matter how you produce your visualizations, the time cost of developing your skills in your chosen medium is going to be what buys you the ability to control and customize what you create. This upfront time investment will also make you faster at producing future graphics in that same medium in the future. So, whenever you're approaching a new visualization problem, you should pick your tools and medium judiciously. You want to balance your immediate needs for speed, accuracy, and reproducibility against your current skill level and the investment in improving those skills in the medium to long term. Unfortunately, the only way to make good visualizations is first to make lots of bad ones and even more mediocre ones first. So sticking on tools then, if your aim is to produce a wide range of high quality visualizations using R, then the ggplot2 package is one of the most versatile and well documented tools that's available to you. The G's at the start of the package name here stand for grammar of graphics. This is an opinionated, abstract approach to constructing data visualizations by building them up slowly and adding additional plot elements one layer at a time. This idea of a grammar of graphics was originally introduced by Leyland Wilkinson, and the paper shown here by Hadley Wickham and the associated R package popularized this approach within the R community. Like many of the Tidyverse collection packages, ggplot2 provides simple but specialized modular functions that can be composed to create complex visualizations. If you'd like to learn how to use ggplot2, I wouldn't recommend starting with the paper, and nor would I recommend starting by using the documentation alone. Instead, what I would suggest is that you work through an introductory tutorial, like the one I've linked to here, or one of the resources linked within the package documentation itself. Once you've developed a basic grasp of the principles used in ggplot, the best way to then improve your skills is to try making your own plots using reference texts and other people's work as a guide. A great source of inspiration here is the Tidy Tuesday Data Visualization Challenge. You can search for the challenge on GitHub to inspect both the plots made by other people and the code that was used to make them. Again, I've added the link here for your convenience. So the second aspect that I'd recommend you think about before getting into a data visualization is where exactly that graphic's going to be used. The intended location for your visualization is going to influence both the composition of your graphic and also the amount of effort that you dedicate to it. So, for example, if you're considering making an exploratory plot at the start of your project, it's only going to improve your own understanding of the structure within the data. You probably don't need to spend much time worrying about refining access labels, color schemes, or exactly which file format to save your work in. If instead you are working on a figure that will be included in a daily stand-up meeting with your team, then you probably want to take a bit more care to ensure that your work can be clearly understood by other people. For example, that the legend and access labels are both large and sufficiently informative. Further refinement again will be needed for this graphic if it's going to be used within an external presentation. Some questions you might want to ask yourself are, is the message of the visualization immediately clear? Will this same graphic still be clear when it's displayed in a boardroom or a conference hall, or will it pixelate? How long will the audience have to interpret the visualization while you're speaking? Even if the slide deck is made available in advance, very few audience members will actually refer to them before or after the presentation. Some opposing considerations have to be made when you're making a visualization for a report or a scientific paper. In this case, plots and tables can actually be very small, particularly if your report has a 2-column or a gridded layout. You have to be really wary about the legibility of your smallest text in this case. So think of things like values on axes, and your visualizations need to be clearly understood, whether that document is being read zoomed in on a computer screen or printed out in black and white. So to ensure that your graphics are suitable for the intended medium, it's helpful to know a little bit more about file types. There's two main types of image file, and these are known as vector graphics and bitmap graphics. Bitmap graphics store images as a grid of little squares, and each of these squares or pixels takes a single solid color. If you take a bitmap image and make it large enough, either by zooming in or by using a really big screen, then these individual pixels are going to become visible. Usually this isn't going to be your intention, so you need to ensure that the resolution of your graphic, its dimensions counted in pixels, is sufficiently large for where it's going to be displayed. Vector graphics, on the other hand, create images using continuous paths and then filling the areas between those paths with flat color. These vector images can be enlarged as much as you like without making the image quality compromised. This is really great for simple designs like logos, which have to be clear when used on both letterhead and on huge canvases like billboards. However, these vector graphics are more memory intensive than bitmap images, particularly when there's lots of distinct colors or objects within the image. This can be a particular problem in data science, for example, when creating a scatter plot with many thousands of data points on it. It can often be useful when you're making plots to save both a bitmap and a vector version. This way you can use the bitmap when you need small files that load quickly, so for example when loading a web page, and you can use the vector graphics when you need your visualization to stay sharp when really enlarged, so for example when creating a poster or when giving a presentation in an auditorium. Our third point is that data visualizations are a tool for communicating information. To make this communication as effective as possible, you've got to target your delivery method to that intended audience. And to do so, you're going to have to know your audience. To make a compelling data visualization, you have to have some idea about the background knowledge that the viewer brings in with them. Are they a specialist in stats and data science? Or does their expertise lie in the area of application? Are these findings that you're showing going to come as a surprise to the viewer, or are they going to act as confirmation of their pre-existing body of knowledge? It's worth considering these prior beliefs and how strongly they're held by your audience when constructing your visualizations. Take the time to consider how their existing knowledge might alter or influence the way that they interpret what you're showing them. On the flip side here, you might be presenting information on a topic that the viewer, at the best case, is ambivalent about, or in the worst case, is actively bored by. In that case, you can take special care to compose your visualizations in an engaging way that captures and holds their attention. So when you're crafting a visualization, you want to require as little work as possible on the part of the viewer. To do this, we can use attributes called pre-attentive attributes. These are things like color, shape, size, and position, and use these to encode our data values. These properties are attributes of lines and shapes that provide immediate visual contrast without requiring any active thought from the viewer. As we'll see, care needs to be taken to ensure that we aren't misleading the viewer with how we use these attributes. This figure here presents a bar chart showing the mean height of males in several countries, but the bars have been swapped out for human outlines. While the visualization has an attractive and minimal design and a pleasant colour scheme to boot, it doesn't do a good job of immediately conveying the relevant information to the viewer. There are three main issues with this plot, and they're all caused by swapping the bars of this plot for male silhouettes, and are strongly associated with the differences in how lengths and areas are perceived by humans. Typically, we make immediate pre-attentive comparisons based on areas, but we can draw more accurate, considered comparisons when comparing lengths. By replacing the bars of this bar chart with human outlines and not starting the height scale at 0, this plot breaks down the proportionality between length and area that's inherent in a standard bar plot. This causes dissonance between the immediate and considered interpretation of this graphic. An additional issue is that the silhouettes overlap here. This creates a sort of forced perspective that makes it seem like the outlines are also further back when they're further to the left, therefore making them seem even larger if this perspective is taken into account. These three issues are important to consider when constructing your own visualizations as well. Are you showing all the values that the data could take, or focusing on a smaller interval to provide better contrast? If you're using the size of a circle to represent a value, are you changing the diameter or the area in proportion to that value? And finally, if you're making a plot that appears three-dimensional, have you done that on purpose? And if so, can one of those dimensions be better represented by an attribute that isn't position? When reducing the dimension of your plot, you may wish to represent that data value using colour rather than position, for example. When selecting your colour scheme, you should keep your audience in mind. If your aim is to compare two or more categories, then you'll have to select a finite set of colours and ensure that these can be easily distinguished. If you're presenting a data value that is continuous, or has an associated order with it instead, then you again have to select your palette to provide sufficient contrast to all viewers of your work. So for example, if you are representing a measurement that has a reference value, so think of something like temperature in centigrade here, in that case, a diverging colour palette might be used to represent the data that are above or below the reference point, in this case 0 degrees centigrade. Be aware though that this requires some cultural understanding about how the colours you choose will be interpreted. So for example, choosing red for cold and blue for hot is likely going to cause a lot of confusion. For a colour scale without a reference point, then a gradient in a single colour is likely going to be your best option here. In either case, it's important to check that a unit change in data represents a consistent change in the colour across all values. This isn't the case for the rainbow palette that we've shown here, which is also neither a single gradient nor a diverging palette. You can see that the green and blue areas are much larger than the yellow and pink, for example. To ensure accessibility of your designs, I'd really recommend you use one of the many available online tools that simulate colour vision deficiency. An alternative approach is to use a pre-made palette that has already considered these accessibility issues for you. A good low-tech rule of thumb here is to design your visualizations so that they're easily understood when they get printed in grayscale. To do this, it means you're going to have to pick an appropriate set of colours or additionally vary things like the point shape, line width, or line types used within your visualizations. When your plots are included in a report, they're often accompanied by 3 pieces of text: the title, the caption, and the alt text. These all help the audience to understand the visualization, but each serves a distinct purpose. A caption is a short description of the visualization and is usually displayed directly above or below the figure or table that they describe. These captions serve 2 main purposes. In a report, the caption can be used to look up that visualization in a list of figures or tables, while the second purpose is to add additional detail that you don't want to add directly into the plot. Alternative text, or alt text, has a different purpose. It's used to describe the content of an image to a person who can't view it. This text is particularly helpful for people with a visual impairment, particularly those who use a screen reader. This is a type of software that reads digital text out loud, but the software can't interpret images. Instead, it replaces an image with the provided alternative text. Alt text is also a valuable asset in cases where an image can't be found or loaded. So, for example, if there's an incorrect file path given, or someone has a really slow internet connection and can't load a large image file. In that case, the alt text gets displayed in place of the image. The purpose of alt text here is really different from a caption. It's designed as a replacement for the image not just a shorthand or to provide additional information. If there's an important trend or conclusion that needs to be drawn from that visualization, and that isn't already mentioned in the main text, this should be clearly identified in the alt text. This sort of interpretation is a key aspect of alt text, but something that shouldn't be included in a caption. Finally then, titles give additional context that isn't conveyed by the axis labels or chart annotations. So having a title of something like a graph to show how x varies with y isn't very helpful at all. You might as well not have the title there. Alternatively, a title can be used like a newspaper headline and can deliver the key findings of the visualization. If you're including this type of interpretive title, make sure that you give the same interpretation in the alt text. Our penultimate point here, and the fourth aspect of a successful data visualization, is that it must tell a story. This story doesn't need to be a multi-generational novel or even a captivating novella. If a picture speaks 1,000 words, then really what you're aiming for here is an engaging anecdote. Your visualization should be something that either through its content or its composition grabs the viewer's attention and alters their view of the world in some way. Telling an effective story in any medium requires planning. How you construct your narrative depends on what effect it is that you want to have on your audience. I'd like to encourage you to think like a data journalist here and go into your work with the intended effect clear within your mind. Is the purpose to inform them of a fact, to persuade them to use a particular methodology, or to entertain them by presenting dull or commonplace data in a fresh and engaging way? In reality, your goal is probably going to be some mixture of these and fall at some interior point in this triangle. If you can clearly identify where this point is, it can help you to present your visual story in a way that works towards your aims rather than against them. On the point of presentation here, it's important to realize that there's no neutral way to present information. In creating a visualization, you're choosing which aspects of the data to emphasize, which get summarized, and what not to present at all. A final crossover with data journalism is that your visualizations are going to be competing for your viewers' attention. You have to compete against everything else that's going on in their lives, whether that's the doorbell, social media, email, or absolutely anything else. You need to establish a clear hook within your visualization to attract your viewers' attention in the first place, and then immediately deliver your core message. This might be done either by adding a contrasting trend line or including an intriguing title. What's important here is that you first lead their attention to the key message you're trying to deliver, and then on to the supporting evidence. You never know how long you have before someone's going to check out. Our final consideration then, when considering how to create visualizations, is to reduce the number of considerations that we actually have to make. This is done by thinking carefully about each of the decisions that you make and writing guidelines so that you don't have to make those choices again in the future. The decisions that you make while constructing an effective data visualization are really quite important and deserve careful consideration and thought. However, this consideration comes at a cost. This is a cost to your employer in terms of the literal financial cost of paying for your time. And more broadly, this is the opportunity cost of all the other things that you could have been doing instead of making these decisions about your plot. To be efficient in our visualization design, we should extend our dry coding principles of don't repeat yourself to this design process as well. We should make choices carefully, document our decisions, and then externalize the cognitive work required in the future. Many companies are really aware of this financial and opportunity cost and provide style guides for visualization in just the same way as they might for coding or written documents. Having these guides not only externalizes and formalizes many decisions that you have to make, but also leads to a more uniform style across visualizations and across the data scientists that are producing them. This helps to create a unified house style for graphic design and a visual brand identity that's easily identifiable. This approach isn't just beneficial to large companies, but can be very helpful for personal projects in the same way. So I'd highly recommend exploring some visualization guides to get an idea of how these are constructed and how you might develop your own version. Unsurprisingly, some of the best guides here are going to come from media outlets. This type of business is used to dealing with writing style guides, and they're heavily invested in creating and maintaining a distinctive and individual style that's shared across all of their writers. These are exactly the sorts of things that you want from a strong data visualization guide. Across all these different examples that I'm giving you, the level of detail and technicality is going to vary wildly. For example, the BBC here doesn't provide any strong guidelines on the details of final visualizations, but they do provide lots of technical tools and advice on how to construct graphics with those in a consistent way across the corporation. They've even gone one step further and written their own theme for ggplot and published this as an R package. Okay, so let's wrap up this video then. Data visualization might seem like a soft skill in comparison to data acquisition or wrangling or modeling. However, it's often effective visualizations that have the greatest real-world impact. It's figures within reports and presentations that can determine which projects continue to be funded, while visualizations in press releases determine whether the results of your study are remembered by the public, and more importantly, whether they're remembered correctly. When constructing visualizations, it's important to consider whether there are existing guidelines out there that can provide helpful constraints to your work and save you cognitive effort. From there, you need to determine a story that you want to tell, and exactly who it is that you're telling that story to. Once this is decided, you can then select the medium and the tools that you use to craft your visualization so that you have the greatest possible chance of achieving your intended effect. And with that, I'll thank you very much for your attention, and I'll see you in the next video.